In this final lecture for the semester, I'll try to give you a brief introduction to nonlinearity and hopefully help you understand what effect it can have on vibration signals and some of the most basic methods that can be used to take a measurement from a nonlinear system and make some sort of sense of it. So first of all, we'll need to talk a little about nonlinearities and the effect they can have. Nonlinearities can come from lots of different sources. One of the most common is bolted joints, friction between the parts. When you bolt two things together, you think of them as being stuck together, but there's actually a finite friction force. And as the structure vibrates, it can exceed that friction force, and you get stick-slip at the joints. We'll talk about an example of not large deformations, what those can do. Another really common example is nonlinear material properties, especially rubber, things like engine mounts, bushings. Those are highly nonlinear materials. And if the deformations are large enough to get into the nonlinear regime, then that needs to be accounted for. For example, I worked on tires a little bit in my postdoc, and there the modulus of elasticity of a tire was said to change about an order of magnitude as you go from stationary to rolling. So anyway, there are lots of other things, magnetic forces in motors and things like that. Aerodynamic forces could be in effect. And these days, a lot of us are interested in micro and nanoscale systems, small scale machines and sensors and things. And at small scales, there are all kinds of forces, nonlinear forces that can become important. So there's a few. We'll focus more on the industry relevant macro scale forces in this lecture. But the world is basically nonlinear. Everything is nonlinear. One famous person who I know, Keith Worden, in the UK, likes to say that separating the world into linear and nonlinear is like separating the world into bananas and not bananas. Right? So everything is nonlinear, but linear models serve us really well, and in lots of industries, we can do a lot with them. But we do need to recognize that nonlinearity can crop up in any system if we push it hard enough. So how does this change the response of a structure? Well, in extreme examples, for example, this projectile hitting a concrete beam, right, here you get shattering, you get pieces that used to be connected that no longer are. So this is a strongly nonlinear phenomenon. And obviously, most of what we've learned doesn't apply to a system like that. In other cases, though, we just have a vibration that makes things happen, and we'll talk about why frequencies can change with time or with amplitude, and we'll cover those types of cases in more detail. One other example of the kind of thing that we won't focus on, a student of mine went to work for Mercury Marine, and he would work on outboard motors, and one thing they were interested in is a motor racing along in a lake and then hitting a log or something under the surface of the water. And so that's an impact event, and it can induce a large stress in different parts of the motor, and they wanted to design their motors to survive that. So we're not really going to cover this kind of thing, but this type of analysis is done quite frequently in industry. This is, it's dynamic in that the loads come from an impact, but it's a little more of a quasi-static problem. It's really the material properties that are nonlinear. It's the plasticity, those kinds of things, which are static phenomena, are what are really dominating the problem. We're going to focus on dynamics and vibration. And so usually the applications we're interested in are noise, fatigue, things like that. One interesting area that I've worked on is the area of hypersonic aircraft. Just to give you a quick intro to what I mean by hypersonic, here's the Mach scale, Mach numbers from 1 to 8. And your typical airplane that we all fly on goes just below Mach 1, 500 something miles an hour. In comparison, the Air Force's SR-71 Blackbird made it past Mach 3. So that can take our trip across the US from 4 hours or something down to 1 hour, just over 1 hour. So, but progress, we're never happy with that, and so the push is for faster and faster vehicles. Now, to put all this in perspective, though, we do have vehicles that have gone at much, much higher speeds. These are the approximate Mach numbers of the space shuttle as it comes on re-entry or Apollo capsule. But those are designed very differently. If you look underneath the space shuttle, there are all these thermal tiles that protect it from the heat and carry the aerodynamic loads. And this was a very maintenance-intensive system. Each of those tiles had to be inspected after a flight. You can see they each have serial numbers. Some of them are replaced after a flight. So there's a lot of reconditioning that goes in. And anyway, this field of research is more interested in vehicles like the SR-71 that can fly over and over again without needing a lot of maintenance. And when you get to those kind of levels, you get really large loads on panels, and that can induce a nonlinearity. And those are important because the stresses depend on vibration amplitude, and a relatively small change in the stress when we're talking about fatigue can cause a huge reduction in life. These fatigue curves are usually on a log-log scale. And so when you get to this threshold of high stress, it can really have a severe impact on life. And again, the nonlinearity we're interested in is basically what happens when if you imagine this panel deforming with large amplitude, what you can get is a bending stress turning into an axial stress. So at small amplitude, it's mostly the bending stiffness that dominates. At large amplitude, you have to stretch the panel to be able to deform it more. And so the stiffness goes up a lot. One really simple example we can work through is a quadratic spring. Here's an example of a stiffness that increases with amplitude. So here we have our mass and stiffness term. If we add in a term with an x squared in it, then as displacement goes up, the stiffness or this forcing term will go up even more. So now this one actually has an opposite effect when you go to negative displacements, and that has interesting consequences as well. But let's just use this as an example because it's algebraically the simplest. So we convert this to a non-dimensional form by dividing through by the mass. And so we can write the equation of motion this way. And as we've covered many times in class, if we want to define the steady state response, we would assume that it has the form of some real part times an amplitude e to the I omega t. We plug this into the equation. If this was the linear case, we would be able to solve for the response x here, and there's a term, remember, in the denominator, the natural frequency squared minus the drive frequency squared. And that's why when the drive frequency is equal to the natural frequency, this is 0 and you get a large amplitude vibration. All right. So what happens now if we include that nonlinear term? We can use the same guess for the response. We'll assume that x is still a single harmonic response. And if we plug that in, everything is proceeding as we're used to, but we have to deal with this beta x squared term. So to deal with that, we have to recall that the real part can be written as the sum of the value in its complex conjugate divided by 2. Right? This form here, if we want to multiply, we have to write it in this complex conjugate form, and then we can square. And when we do that, we get the first term squared I just pulled the 2 to the outside. We get 2 terms that are the cross between these two. And notice both of those terms, the I omega t's cancel, so we get e to the 0. So these are constant terms. And then we get this term, which is a complex conjugate of that one. So if we rearrange this, we got a term that has 0 frequency, and then we have a term that's oscillating at 2 omega. That's the combination of these two complex conjugate terms. So we plug all that into the equation, and now we have lots of things going on. We have a term that's constant. We have terms that are oscillating at e to the I omega t, and a term that's oscillating at 2 omega t. And if you think about this, the constant term can't change what happens at omega, right? So these terms here have to satisfy themselves regardless of what happens with this term. Similarly with this, right? This is at a higher rate. And so over a long enough amount of time, it can't have an influence on any of the other terms. So this leads us to this concept of harmonic balance, which is that we can take each frequency one at a time and pull them out of the equation and satisfy them separately. So if we do that here, for example, if we pull this term out, or all the e to the I 2 omega t terms out, we get this. This tells us that this vibration is only possible if beta equals 0. Well, that's not very good. That's not very interesting, right? Similarly, this term, this constant term also tells us that we have to have either 0 vibration amplitude or 0 nonlinearity. And if that's the case, then we're back to the linear solution. So that didn't seem to help us very much. But that same procedure actually can be useful for other systems. And it actually did help us in that it told us some important things. One, that the underlying linear system, nothing changed. So the natural frequency is still the natural frequency, even if we have non-zero vibration amplitude. It also told us that we can't have a response that's an e to the I omega t. We need to have higher harmonics. So to really solve this, we'd have to move these terms to the other side and account for the fact that the response could have frequencies of 0 omega and 2 omega, even though we're only exciting at omega. So this is one of the first phenomena that we see in nonlinear vibration. This is like a forcing term, and so the nonlinearity introduces higher harmonics into the response. And so one simple test for nonlinearity is to look for higher harmonics in the response. And sometimes that can be pretty effective. So that was the first lesson. The second was that this particular type of nonlinearity won't change the effective natural frequency of the system. If we took those two terms and we repeated the process with a cubic nonlinearity, so an x cubed rather than x squared, I won't go through all the details because it's a homework problem and because the math, it's the same idea, just more math. But just point out what happens. When you do it with the cubic nonlinearity, you get a term that looks like this. We have complex amplitude squared times complex conjugate of the complex amplitude. So if we recognize that x star is just the magnitude of x squared, we can rewrite that term like this. And then when we go back to balance the terms at e to the I omega t, we will have an additional term. So if we write that equation, we get this. Note this was our mass term. We have now two stiffness terms, and one of them depends on vibration amplitude. And then we have the forcing term. So this tells us that this term has to be our effective natural frequency squared. Or in other words, the natural frequency, the effective natural frequency depends on vibration amplitude. And this is the second important observation we can make about nonlinear systems. The frequency of vibration will, in general, depend on the vibration amplitude. And we can also show that damping can also depend on vibration amplitude, but we'll get there in a while. So this leads us to a new way of seeing nonlinear systems. And it's to look at the frequency and amplitude or energy. And Rosenberg in the 60s pioneered a definition of a mode that allows for including both of these. Basically, you can think of a nonlinear mode as any solution to the undamped, unforced equation of motion. And if you think about it, that's the same thing we would do if we had a linear system, right? Omega 1 would be the solution when we have only these terms. So now we allow the stiffness nonlinearities to come in. And a nonlinear mode then is defined as any solution to that. And they're amplitude dependent, so we can plot them as a curve where the effective natural frequency is a function of amplitude, or vibration amplitude, or energy in the system. These are useful because if we were to go and solve for all the forced responses where we have the damping and the forcing terms back in there, we see that at the peak, so these are, this is the forced steady state response at different vibration amplitudes computed numerically, and we see that they track the NNM. So the natural frequency is always the frequency where the vibration amplitude is largest, and that's true for linear systems and for nonlinear systems. So this is a really powerful concept, but we have to give our disclaimers first. Nonlinear modes are not orthogonal in general, so we can't use them to write our coupled set of equations as a bunch of uncoupled 1 degree of freedom equations. There aren't yet any superposition principles. There are cases where superposition applies, but there aren't yet any general superposition principles that can be used to find the response. And so these are more limited, but they do give us a lot of insight. How do we compute NNMs? I don't want to go into the detail, but we basically solve for the steady state response numerically at a certain amplitude, and then we can make a guess where the next solution might be and apply corrections, and we can basically find a branch of solutions. I won't go into the details. There's actually a whole literature with lots of methods and lots of different options, though a lot of them share these kind of ideas of solving nonlinear optimization problems using this idea of taking a known solution, predicting where the next one might be, and then correcting. So I won't say any more about that. One thing that our group actually worked on was a way of extending these methods to huge structures where you have maybe thousands of degrees of freedom, such as a finite element model like this panel. This is a panel that was studied by the Air Force. Large deformation vibration in the skin panel here of this airplane could lead to nonlinearity, and we wondered if we could calculate its nonlinear modes. So again, I won't go into the details, but basically we took an algorithm similar to what was on the previous slide, and we wrapped it around a commercial finite element package. And there were some tricks we had to do to get around to deal with the large number of degrees of freedom. I won't go into those here, but it basically involved applying a static force to the structure, finding a static response, and that static force was in the shape of a mode, and then using that as an initial condition when we integrated the system. Anyway, long story short, we were able to develop an algorithm that could do this. Here's one of our initial test cases, a clamped clamp beam. This is one of the simplest geometrically nonlinear structures you can study. And again, geometric nonlinearity means as the beam vibrates at low amplitude, it's the bending stiffness that matters. But at larger amplitude, it has to stretch, or you develop a tension in the beam that stiffens a lot. And so that increases the effective natural frequency. So using this algorithm, we were able to compute the NNM, or the natural frequency of that beam, as a function of vibration amplitude. And let's look at what those results look like. So here's mode 1 and mode 2 of that beam. And again, natural frequency versus vibration amplitude. And so what these results show us is what happens when you have a nonlinear structure. At low amplitude, this is a linear mode of a clamp-clamp beam. And notice that all the nodes are just moving up and down. Let's first look here. At really high amplitude, we get something very similar. But if you look really closely, you can kind of see the shape flattening out in the middle due to the stretch, due to the nodes having to move both laterally and up and down. And the beam is really stiff laterally, so that causes a big increase in the natural frequency. Now, the other thing, though, that can happen is that you can get higher modes excited, or coupling between the modes, and this is called an internal resonance. And that, again, comes about due to these terms on the right-hand side of the equation. So let's just look back really quickly and remember. Right, we can think of the nonlinearities as causing forcing terms on the right-hand side of the equation. So this term, if 2 omega happens to be a natural frequency of the system, of a multi-degree of freedom system, then this term will excite another mode. And that's how we get coupling between the modes. Okay. All right, let's skip ahead here. So anyway, so this gives you an idea of what nonlinear structures will do. In some ways, they're very similar to linear structures, just with a frequency that depends on amplitude. But there are these very interesting things that can happen. Here's a summary on the first 3 modes of the beam. You can see the various internal resonances that can pop up. These plots show the deformation in the beam, so low amplitude, very little axial stretch in the beam. At high amplitude, the color bar shows us we get a lot of axial stretch in these regions. And then in the internal resonances, we get higher modes excited. So you can understand a lot about nonlinear dynamics if you can just understand this one beam and these different phenomena that happen. So this algorithm that we developed can potentially be used for larger scale structures. Here we were interested in studying this plate, which is part of an exhaust system. Air flows through it, and that can excite vibrations, and we suspected there might be a nonlinearity. And so even a relatively large finite element model like this, we're able to do the same kind of calculation and tell our employer how much will the frequency change over the range of vibration amplitude you expect to see in service. If the change in frequency is large, then you might need to account for it. If it's small, we can approximate it as linear. Here are the deformation shapes for this plate. And one thing that was interesting here is that at high amplitude and the large vibration, you get kind of a redistribution of stress that can actually change the point where the peak stress occurs. So that can also be important. All right, but you saw the 2 key phenomena, and you saw that these scale to all kinds of structures, beams, plates, and almost anything you can imagine. You could kind of see these same kinds of phenomena, and you could quantify them by thinking about nonlinear modes of vibration. One of the most common sources of nonlinearity, though, is actually friction in bolted joints, bolted interfaces. Most things that we are interested in are thick enough that the geometric nonlinearity isn't a problem unless you're in a really extreme environment. But all kinds of structures have nonlinearities due to friction. And we've covered that one first because we see the full range of things that can happen. We'll see that joints often can be treated in a more simplified way. So just a note on the status. So joints are present in all kinds of structures. Here are some examples. And they really are a challenge. They increase the cost required because, for example, if this engine was a solid piece of metal, I could trust my finite element package to predict its dynamics, its modes of vibration really well. But because we have all these bolted joints and contact interfaces, it becomes much more difficult, and we rely on testing, prototyping to make sure we get that right. While we haven't yet figured out how to model and predict what happens in joints, there have been some interesting cases where we remove joints from structures and see that it made vibration worse. One is the F-22. The tail was replaced with the metal, aluminum or titanium tail was replaced with carbon fiber, which theoretically carbon fiber has more damping than a typical metal. But because it was a composite construction, the joints were glued rather than riveted or fastened in the usual way. And so because the joints were taken out of the equation, there were actually lower damping in this structure than there would have been in a conventional tail. And initially, this airplane had issues with fatigue of the tail. There were also aerodynamic problems and other things. I've heard stories where this has been seen in different jet engines in the outside housing of the engine when that's redesigned and the joints are moved around, that we can get vibration problems occurring that didn't used to occur because the dissipation due to the joints changed. And this is interesting to think about because these days, when we're thinking about 3D printing all kinds of interesting geometries, we could potentially maybe think of making an airplane out of one solid piece of metal. And we know, though, that that would probably have some significant consequences because the joints, we would lose all that damping that the joints are typically giving us. Okay. So what happens with nonlinear interfaces? You like to think of bolts as just gluing two surfaces together, but in reality, when we preload a joint, we get high pressure under the bolt, and the metal wants to behave like an eraser and wants to peel away as you get away from that due to the Poisson effect. And so you end up with areas of high pressure and areas of low pressure. And at some point, the pressure becomes low enough that even under small amplitude vibration, you can get stick slip happening in the joint. So if we think of an engine, then we could zero down to the scale of each bolt. And now this is telling us that around each bolt, it's actually a small region where the friction would be important. And if we were to zoom in even more, we could think about the roughness of the surfaces, even the chemistry or the actual atomistics there. So this is a really challenging problem because the scale of the joint and the scale of where the nonlinearity occurs is so small relative to the structure. Just to bring this example a little farther, here's a result of a finite element model where we have a cantilever beam vibrating up and down, and we have a bolt holding it together. And this just kind of shows you what happens. The red is the area that's in contact, the green and stuck, the green is the area that slips. And as the amplitude of displacement of the beam goes up, you get more and more of the area slipping. Fortunately, though, and you can kind of imagine that if you look here, most of the preload stays there. We're only losing a little bit of the contact area for typical vibration levels. And so the change in the natural frequencies with bolted joints tends to be really pretty small. Here's an example measurement, and we'll talk about more about this in a minute, but the basic idea is if you think of a natural frequency, And as vibration amplitude goes up, you get that natural frequency decreasing due to the decrease in stiffness as the joint slips. But that decrease tends to be pretty small. And the modes tend to remain uncoupled, and we don't see a lot of higher harmonics. We don't see a lot of the crazy phenomena that we saw with the other structures. As a result, with these structures, we can often take a complex structure with lots of bolted joints, and we can actually represent that mode by mode, and represent each mode with a 1 degree of freedom system that might be nonlinear, that may have nonlinear stiffness and damping, but we can ignore coupling between the modes in many cases. And when that's the case, and the reason for that comes from harmonic balance, and I won't go through the details, but basically, if we have an equation of motion, we have some nonlinear forces due to the joints. And say we're vibrating harmonically so that we write the joint forces as a Fourier series, right? If the vibration of the structure is harmonic and the joint forces depend on the displacements, they will also be harmonic. So we can treat that as a forcing term, and we can see that if we're thinking about one mode of vibration, this forcing term will only matter if one of those harmonics lines up with the natural frequency. If the harmonics are not integer multiples of each other, if the natural frequencies are not integer multiples of each other, we can ignore that modal coupling. Anyway, a more detailed way of saying that we'll approximate the structure in this very simple way where each mode is just a 1 degree of freedom system. If we can do that, then we can do testing kind of as you've done before. We can apply, say, an impact force, we get a response, and then we can break that response into a bunch of modes. Assuming the mode shapes don't change, for example, we could use a modal filter. And then if we were to use, if we were to look at the signal from each mode and use log decrement to figure out the damping ratio as a function of amplitude, and say the period change to get the frequency versus amplitude, we could characterize each mode in terms of its natural frequency and damping and how those depend on the vibration amplitude. And we could even fit a model to each mode that might replicate that behavior. So here's one example that we did in our group, a test on 2 beams that overlap in this region here. And so there's 4 bolts holding them together there. So we suspended with bungees and used a laser vibrometer to do the test. And as we look at the first mode, we saw this kind of behavior where we had the frequency going down, but only a little bit, right? This is a pretty small nonlinearity, but the damping actually went up quite a bit as vibration amplitude increased. And since then, we've seen this same behavior on lots of structures. Here's another example, 2 catalytic converters from automotive exhaust system. These would usually bolt on either side of the engine. Here, replace the whole engine with just one little piece of metal. But you still get interesting dynamics of these flexing back and forth when it vibrates. And if we look at a particular mode, using various different force levels, various different places to excite it, we saw pretty consistent behavior, which tells us that for this structure, we could think of, we only need to worry about one mode of vibration and its amplitude. And if we knew the vibration amplitude, we would know the damping, and we could get a good understanding of what would happen. Okay, so you've seen various examples and various little bits of theory. We haven't done it justice. And now we can start to ask, what do we do experimentally to tell if we have a nonlinear system? So there are a few different methods, and there's a great reference here if you want to read up on more. But some of the simplest methods are really well within your grasp and things you can already do. Let's start with the homogeneity test. The idea here is if we have a linear system, then the modes won't depend on amplitude. And so the FRF you get will be independent of how large of a force we apply. So here they had a cantilever beam with a thin strip, which gives us a geometric nonlinearity, like what we saw with the hypersonic panels a minute ago. So in this case, they measure the FRF using a small level of force, and then they measure the FRF using a large level of force. And if those two FRFs are different, then that gives you an indication that there's a nonlinearity. And the amount of shift that you get tells you something about how strong that nonlinearity is. So here they did that around the first mode and on the second mode, and they're able to see that, yeah, this system definitely is nonlinear at a 22 Newton forcing amplitude. So that's the most basic approach. Just check consistency. You can do this with the hammer as well, just hit at different amplitudes. Here's an example of what this looked like for a bolted structure. We had 3 bolts on a beam, and hitting it at different peak force levels. If we calculate the FRF at a point in each case, you can see the FRF changing shape. We're introducing a distortion in the shape, and this shape is actually pretty common for bolted joints. And you see that the amplitude is going down, so there's an increase in the effective damping. So a simple test like that can really easily tell you if you have nonlinearity. There are some other methods that can be used. One of them is coherence, which in the process of computing an FRF, it's a measure of consistency in the autospectra that go into that computation. So it gives you an idea of the variability. If you have high variability, then that probably means that you have amplitude that's changing with time throughout the course of your test. So, so that can sometimes be a useful metric. The problem with coherence is that there are lots of other things that give you bad coherence. As you probably saw in the lab, a little bit of leakage can also decrease your coherence and cause problems. And so that that can also be a cause of low coherence and not nonlinearity. Okay, there's other kinds of tests. One, reciprocity, that applying an input at one point and a force at another point should give you the same FRF as applying a force at a different point and measuring the response at the input point. Anyway, other methods that can be used as well. But one of the most common is this homogeneity test. This is done almost any modal test that I see. They'll usually do a homogeneity test to see if the results are consistent and amplitude dependent. If they're not, then we can go forward confidently with a linear model. Another approach is time frequency analysis. What I was kind of hinting at earlier, if we have a single mode response, we can look at how the frequency changes with time. So here you can see a high frequency going to a low frequency. And so we can characterize that, and that can give us an idea of the nonlinearity in the system. And the Hilbert transform is a good tool that can be used to do that. Another one is a spectrogram. The idea behind a spectrogram is that rather than taking the FFT of a full signal, let's break it into short blocks and apply a Hanning window and take the FFT of just that block. Then we can compare all of these FFTs and see if the frequency content has changed. So that's a spectrogram. A wavelet is a similar idea, but they use different different combinations of window functions and harmonic functions that give some what can be better mathematical properties, but both give pretty similar results in the end. There are times when this method can give beautiful results. For example, this 2 degree of freedom analytical system was simulated with super light damping, I think 0.0004001%. But anyway, if you excite the system and you look at the different modes, these are the two low-level linear frequencies. And you can see all kinds of frequencies coming up, and you can see how the frequencies evolve as vibration amplitude goes up, going back in time. And so you get a wealth of information from one transient response. But again, this was a simulated case where we have tiny damping. When you use this in practice, you tend to see something much muddier like this, because the damping is high and it causes the frequencies to change relatively quickly. And so it's typically difficult to make a lot of sense of these kinds of measurements. But often you can get at least some useful information from them. Here's another example of the nonlinear joint. I showed you this earlier. And I'll use this to introduce one other time frequency method that we developed. And the idea is a method that's geared towards transient response or impact excited response. So in that case of free response or transient response, you start out with high amplitude vibration, and the vibration amplitude goes down with time due to damping. So the idea is that one of my collaborators came up with was to take the signal and just to erase the first part. So we take the FFT of the whole signal, then we erase the first part, create a new signal, take the FFT of that, and we can erase more and more of the signal and see how the FFT evolves. And this is actually what gave the signal that I showed you earlier. So if we took the FFT of the whole signal, we get this distorted shape, smeared shape that shows us that there is nonlinearity. And as we erase more and more, this is the number of milliseconds of response that's been erased. We eventually see this converging in the red lines down here to what looks like a nice linear resonance. So we can say at this vibration, at this time and onward, the system was behaving linearly. And so we can use that to figure out what amplitude the nonlinearity starts at. So this is a really easy method and something that you can use if you want to, and you're really simple to code up, and we have code that implements it as well. So looking at more globally, that was just one of the modes we were looking at. If we look at different modes, we can see nonlinearities. And again, all of this comes from just one transient signal, so you can get a lot of information out of one signal, and everything looks a lot like the FRFs that we're very used to. And so it's easy to make sense of. All right, here's a finite element model just showing what's happening. So this mode that we're exciting here, I believe it's this one in the finite element model. And so as the beam bends, there's a moment that gets applied to this block, and that causes a little bit of slipping in the joint that causes the stiffness to go down. All right, there's a little more we did looking at using one of the later responses to predict what the response should have been backwards in time if you've been linear. This is another tool we developed that can sometimes help to, really it helps you to interpret the curves, but it can sometimes help you to detect nonlinearity. So here, for example, when we fit the red, we see that the yellow was still behaving pretty linearly, but if we go to earlier times, there's a definite nonlinearity. All right, so there's your introduction. A few references. These are two great papers to give you an introduction to the field. They're fairly recent. There have been some advances since then, but they will give you a really good idea of what's going on. Here's a reference for the algorithm I talked about at the end. And really, I recommend, if you want to learn about this, consider taking EMA 747, the class on nonlinear vibration. And we'll go through all these topics in a lot more detail. And with that, I hope you have some idea now what nonlinearity can do to a system and what to watch for, and some of the basic methods that can be used to post-process measurements and to analyze and try to characterize a nonlinearity.